In chapter 12, we're going to be discussing redox reactions. And the interesting thing about redox reactions is that they are so applicable because they involve something that we use practically every day, which is batteries. I can't imagine that a day goes by where you don't, in some way or another, use something that's got a battery in it. So what we're going to be learning in this chapter is going to explain a lot to you about how a battery actually operates. But before we can do that, we have to talk about oxidation numbers. What is an oxidation number? Well, you're familiar with charges, which is what you get when an atom gains or loses electrons. Now, an oxidation number isn't exactly like a charge, but it is similar. Oxidation numbers don't actually exist. But it's a tool that we use so that we can understand the mechanics of how some of these reactions take place. The actual definition of an oxidation number is if you have a bond between two atoms, and then if you assume that the more electronegative element takes control of all of the atoms that are being shared, then that change in the number of electrons it is currently possessing is considered its oxidation state. So let me show you exactly what that means. Okay, what I have up here, if I can get the camera so you can see it, let me just rewrite it so it's a little bit lower. If I have a carbon dioxide molecule right here, and I look at the periodic table, carbon, which I have a portion of the periodic table drawn right here, carbon is here and oxygen is here. And if you remember the electronegativity trends that we studied in an earlier chapter, electronegativity increases as you go up and as you go to the right. So oxygen is going to be a much more electronegative element than carbon, and it's going to want to pull the electrons toward itself. So in the carbon dioxide molecule, the carbon initially started out with 4 electrons in its valence shell. The oxygen initially started out with 6 electrons in its valence shell. So because oxygen is more electronegative, it's going to pull the electrons toward itself. So the oxygen is going to pull both of these pairs of shared electrons toward itself, and in place of having 6, it's now going to have 8 electrons around it. So going from 6 electrons to 8 electrons means that this is now going to have an oxidation state of a -2. This is going to be the same way. This oxygen is going to pull all of the shared electrons toward itself, and so this is also going to have a -2 charge or a -2 oxidation state. It's a little bit different than a charge because we're going to assume that all the electrons get pulled towards it. The carbon has now gotten all of its electrons pulled away from it. It had 4, now it doesn't have any, and so the oxidation state for the carbon is going to be a +4. Now, the good thing about this is that you don't have to draw a dot structure every single time you need to determine oxidation states for electrons, oxidation numbers for atoms. So instead, you have a series of rules that is on page 360 of your textbook. And those rules, while a few of them are always true and a couple of them are sometimes true, you can use them to figure out what the oxidation numbers are for nearly any compound that you're going to be given. So we're going to do several examples so that you can understand how to assign oxidation numbers. Okay? We're going to start with something like copper iodide. Most of the time, a group 7A element is going to have an oxidation state of -1. And you're already familiar with transition elements like copper, which we don't always know what the charge on them is going to be. So with oxidation states, generally you have to go by the general rule. I'm going to assign what I do know, and then you're going to have to take what's left over and to figure out what's going to be the rest of them. So for copper iodide, the oxidation state of iodine is going to be a -1. And the cardinal rule here is that everything has to add up to be 0. If you have an ionic compound or a covalent compound that does not have a charge attached to it. So if this is -1 and the whole thing has to add up to 0, the copper is going to be a positive 1. Now that doesn't really look too much unlike what we were doing when we were learning how to name compounds, because you figured out that this would be a positive 1 charge, and so therefore you would name this one as copper 1 iodide. So again, this should look similar to you already. If I look down here at FeBr3, again, you've got a transition metal with a group 7A element. The bromine is going to be a -1. I have 3 of them, so 3 and a -1 is a -3. So my iron is going to be a +3. Okay. Now let's look at ammonium chloride. This is a polyatomic ion that you should recognize. It was one that you were supposed to memorize. So let's start with what I do know. I do know that hydrogen, this is one of the rules that's in the textbook that you'll see there. The hydrogen is going to have an oxidation state of a +1. And your 7A elements normally have a -1 oxidation state. So this will be a -1 here. So what have I got? I have 4 positive ones, which gives me a +4. The chlorine's a -1. When I add that together, that's a total of a +3. The whole thing has to add up to 0, so that means my nitrogen is going to have an oxidation state of -3. Let's look over here at KClO3. Okay. Oxygen almost always has an oxidation state of -2. There is an exception where if it's in hydrogen peroxide, it has a slightly different oxidation number, but most of the time, oxygen's going to have an oxidation state of -2. So I'm going to put a -2 up here. Potassium is in the first column of the periodic table, so the potassium is going to have an oxidation state of a +1. Now, we said before, and in the ammonium chloride, the chlorine had an oxidation state of -1, but you'll notice that here, that wouldn't work. Everything would not add up to 0 in a case like this. So here, the chlorine is going to be different. So I have 3 times a -2, which is a -6 for the oxygen, a +1 for the potassium, and so that gives me a -5 if I add them together. The chlorine then is going to have to be a +5 in order to make everything add up to 0. So the rule that says that the 7A elements usually have a -1 charge, you can see that that's true here because chlorine obviously does not have an oxidation number of -1 like you would expect it to. Okay, let's look at BRF5. This is another similar example. We know that fluorine always has a charge of a -1, so that means that 5 times -1 is a -5. Well, in order for this to add up to 0, the bromine is going to have to be a +5. It is a 7A element, but it's not going to follow the rules in this case because the fluorine rule kind of overshadows the other one or outranks the other one. Now, all of these so far, we've had to have it add up to be 0 because there wasn't any kind of charge on the molecule as a whole. This one's different. In fact, you may recognize this as a carbonate ion. And so I have a carbon and 3 oxygens, but all together, they have a -2 charge on the whole thing as a unit. So what that means is that when I add together the oxidation numbers, they have to add up to a -2. Oxygen, just like we talked about up here, oxygen is going to have a -2 oxidation number. So 3 times a -2 is a -6. But altogether, this has to add up to a -2, so that means that my carbon is going to have to be a +4. Okay. Finally, we're going to look at calcium perchlorate. This one's a little bit trickier. There's no charge on the whole thing, but there is a polyatomic ion here, and there's really a couple of different ways that you can do this problem. We know that calcium is in the second column of the periodic table, so it's going to have an oxidation number of a +2. Oxygen is going to have an oxidation number of a -2. Now again, 2 different ways you could look at it. One way that I could look at it is to say, well, if this is a +2, this is not a polyatomic ion that you memorized, but you can tell by looking at it, If the calcium is a positive 2, then each one of these must have a charge of a -1 on them because there are 2 of them and would have to add up to 0. So if I look at what's within side the parentheses as far as the polyatomic ion goes, 4 times the -2 gives me a -8. And if I need the whole thing to add up to a -1, the chlorine is going to have to be a +7. Okay? So that's one way to think about it. Another way to think about it would be like this. If I know that the calcium is a +2 and the oxygen is a -2, 4 times -2 gives me a -8. But I have 2 of them, and so 2 times the -8 would give me a -16. So if an oxidation number of -16 and an oxidation number of +2 is going to give me a difference of a +14. So that means the chlorine has to give me a total of +14, but again, there are 2 of them in order to do that job. So each chlorine, if I would divide that through by 2, each chlorine is going to have to be a +7. And you can see those are the same numbers that I ended up with the first time I did it. So whenever you're doing something that's more complex like this with a polyatomic ion, you can either look at it as what the polyatomic ion needs to be, or you can look at it as a whole with what the entire molecule is going to have to be. If you want to look at it as a whole, then the whole thing will have to add up to 0. If you want to look at it just in terms of the polyatomic ion, then what the charge is in the parentheses will have to add up to whatever the charge on the ion is, very similar to what we did when we did just the carbonate ion over here. So your assignment for today is going to involve doing a number of different examples like what I just did, where you're going to be assigning oxidation numbers.